The last thing we're going to do in this lesson is talk about how to compute probabilities using the multiplication rule. First, let me introduce you to the multiplication rule. Here's the first thing that you should know about the multiplication rule. The multiplication rule is used to find the probability of A and B. The probability of A and B can be computed in different ways. We have computed the probability of A and B in the past without using the multiplication rule. If you're given a contingency table, you can find the probability of A and B by just looking at the values on the table. So again, just because you have the probability of A and B, it doesn't mean that you need to use the multiplication rule. So be careful. Sometimes it's easier to just look at your outcomes to find this probability, or to just look at the contingency table that you're given to find the probability of A and B. Let's be careful here. If you know that two events are independent, if you know that two events do not affect each other, then the multiplication rule states that the probability of A and B is equal to the probability of A times the probability of B. We can only use this formula if we know the events are independent. If the events are dependent, then the probability of A and B is going to be the probability of A times the probability of B given A. Notice the formulas are very similar. We have the probability of A first, and then we multiply by the probability of B. Now, when the events are dependent, when we calculate the probability of B, we're saying, remember that A has happened. So here we have the probability of B given A has occurred. We're going to see how those probabilities play out in different scenarios. For now, just make a note to yourselves. If I know that the two events are independent, then I'm going to use the probability of A times the probability of B. If I know that the events are dependent, then I'm going to use the probability of A times the probability of B given A. The last thing that I want to emphasize here, which is something that we have seen before, is that if two events are mutually exclusive, what does it mean for two events to be mutually exclusive? That means that they cannot occur at the same time, cannot happen at the same time. Again, if two events are mutually exclusive, that means they cannot happen at the same time, then we simply say the probability of A and B is 0. Here, what I'm trying to emphasize is that if you know that two events cannot happen together, don't waste your time. Don't try to set up the formula, the probability of A times the probability of B, or the probability of A times the probability of B given A. You would simply just write the probability of A and B is equal to 0. They cannot happen together. So here's my recommendation. Whenever you look at the probability of A and B, the first question you should ask yourself is, can the events happen together? Or can they happen at the same time? If the answer is no, they cannot happen at the same time, then you simply write the probability of A and B is equal to 0. Now, if the events can happen at the same time, then you ask yourself, can I see the number of ways A and B can happen from looking at a contingency table that is given to me, or from looking at the possible outcomes from the sample space, right? If you can simply see the number of ways A and B can happen, then go ahead and use that. Now, if you cannot see the number of ways A and B can happen, then you can go ahead and ask yourself, are the events independent or dependent? And that is going to help you determine which of these two rules you're going to use. The probability of A times the probability of B, or the probability of A times the probability of B given A. I'm going to walk you through that thinking process when we look at the exercises here below. Let's go ahead and compute probabilities where we're being asked to compute the probability of A. First, we're going to consider rolling a die and picking a card from a deck. So we have two different experiments here, rolling a die and picking a card from a deck. Here we're being asked, what is the probability of rolling a 3 and selecting a king? Notice here, we see the probability of rolling an 8 and selecting a king. So here, I'm already thinking about how we need to compute the probability of A and B, where A is the event of rolling a 3 and B is the event of selecting a king. Okay. So again, here I'm saying, what is the probability of A and B? You should be asking yourself, can the events happen at the same time? The answer is yes, they can happen at the same time. So here, if they couldn't happen at the same time, then we would say the probability of A and B is equal to 0. Okay, but that is not the case. Next, we're going to ask ourselves, can you see the number of ways A and B can happen by looking at the sample space or looking at a table. I'm not going to write that here because we don't have a table. The answer to this question is maybe I can go ahead and list out all the possible outcomes of rolling a die and picking a card from a deck of cards, but that's going to take me a long time. So I'm just going to say no. I'm not going to take the time to write all the possible outcomes in the sample space. So here my next question is, are the events independent or dependent? Is rolling a die and getting a 3, if that happens, is that going to affect the probability of me picking a card that is a key? Okay. Here I'm asking you, is A going to affect the probability of B? Or the other way around, right? Is selecting a key, if you select a key, is that going to affect the probability of rolling a 3? The answer is no. They don't affect each other. They're two different experiments, right? I can go ahead and roll a 3. That's not going to affect the probability of me selecting a key. So here, without having to prove that the probability of A given B is equal to the probability of A, we can say the events are independent. With that being said, we're going to use the probability of A and B is equal to the probability of A times the probability of B. So let's write that. We can use the probability of A and B is equal to the probability of A times the probability of B. Now we're ready to compute the probability. Let's go ahead and think about what is the probability of A. What is the probability of rolling a 3? You have one single die. How many ways can you get a 3? There's only one way to get a 3, right? There's only one face on the die that has a 3. Now here I'm going to divide by the total number of outcomes in the sample space. Here we're talking about the sample space from rolling a die. We have 6 different outcomes. You can either roll a 1, a 2, a 3, a 4, a 5, or a 6. So here I'm going to write 6. We're done computing the probability of A. Now let's go ahead and compute the probability of B. B here is selecting a king. How many king cards do you have in the deck? You have 4. Now what's your sample space? Your sample space is all 52 cards. Thus, there's 52 outcomes in the sample space. You can go ahead and enter this expression on your calculator. Go ahead and enter 1 divided by 6 times 4 divided by 52. You could also do some of this work by hand. For example, I know that when I multiply fractions, I multiply across the numerator and across the denominator. So I can go ahead and simplify this by hand. Here on the numerator, I have 1 times 4, which is 4. On the denominator, I have 6 times 52, which is 312. Again, this is just some simplification that I'm doing by hand. You don't have to. You can simply enter 1 over 6 times 4 over 52 on your calculator. Let's go ahead and round to 4 decimal places. We should be getting 0.0128. We could also write this as a percentage. We could also write 1.28%. And so we'll say the probability of rolling a 3 and selecting a key is 1.28%. Let's go ahead and consider another example. Imagine you're flipping a coin 2 times. Let me fix that. Okay. Again, here we're considering flipping a coin 2 times. What is the probability of getting 2 heads? Okay. Here we're wanting to find the probability of getting a heads first and a heads second. That is the probability that we're wanting to find. The first thing we're going to ask ourselves is, can the events happen at the same time? The answer is yes. We could flip the coin once and get a heads, and then flip it again and get a heads. Here we know that the probability of getting a heads first and a heads second is not equal to 0. Now the next question is, can you see the number of ways A and B can happen by looking at the sample space? Okay. Can you see the number of ways you can get a heads first and then a heads second by looking at the sample space? In this case, the answer is yes. We can think about all the possibilities that we can get from flipping the coin twice, right? We can get heads, heads, head, tails, tails, heads, and then a tails and a tails. Thus, we can go ahead and compute this probability, right? The probability of getting a heads first and a heads second. Notice that is one of the outcomes, HH. One out of the outcomes. divided by the total number of outcomes that we have. Here we have a total of 4 outcomes. That is how we can compute the probability. Here we're done. The probability of getting a Hertz and a Hertz is 50%. We are done. Now you might be wondering, would it be possible for us to use one of the rules here above? The answer is yes. So I'm going to continue showing you how you can do this, okay? So you could ask yourself, are the events independent or dependent? If I flip a Hertz first, is that going to change the probability of me flipping the coin again and getting a Hertz? No, right? They're independent. Each flip is independent from each other. One flip is not going to affect the second flip. Okay? So here the events are independent. That means we can use the probability of A and B equal to the probability of A times the probability of B. If you're using the multiplication rule, you will ask yourself, what is the probability of getting a Hertz first times the probability of getting a Hertz second? So let's start with the first flip. If you flip the coin, what is the probability of getting a Hertz? That is 1 out of 2. Okay? One outcome is a Hertz out of the 2 outcomes. The 2 outcomes that we have here is Hertz, the other one is Tails. So we'd have 1/2 times, what is the probability of getting the coin, flipping the coin again, and getting a Hertz? This would be, again, 1/2. If we multiply this, we get 1/4, which is equal to 0.25, which is 25%. Which makes me see that I made a mistake earlier. 1/4 is 0.25, which is 25%. So go ahead and fix that. I'm sure you were looking at that mistake and thinking I was going to leave it like that. Okay, so again, 1/4 is equal to 0.25, which is 25%. Okay? Here, I wanted to show you 2 different ways of how you can do this. I would probably go with this first method because it was really easy to list out all the outcomes in the sample space. However, if it wasn't easy for me to list out those outcomes, I would go with the second method. I would say the events are independent. Let's use the probability of A and B equal to the probability of A times the probability of B. So far, I have shown you 2 examples where you can use the multiplication rule, the probability of A and B equal to the probability of A times the probability of B. I have 2 more examples that I want to do with you to show you cases where we're computing the probability of A and B, but the events are dependent. They do affect each other. Okay? So let's go ahead and consider exercise number 4. You're going to consider the event of picking 2 cards from a deck of cards. Notice here, we're not just picking 1 card, we're picking 2 cards. We should be wondering, are we replacing the first card or are we not replacing the first card? Okay? And so we have both scenarios here. Let's go ahead and look at part A. What is the probability of selecting 2 black cards with replacement? Okay? So we have all 52 cards. You're going to imagine that you select one and that first one is a black card. Then you put it back, you select another one, and you get a black card again. Here, we're wanting to compute the probability of black first and black second. You can also write black and black. I'm just wanting to emphasize that we are doing this twice. We're selecting a card twice. I'm going to go a little bit faster for this example. Ask yourself, can the events happen at the same time? The answer is yes. Can you see the total number of outcomes in the sample? Can you count how many possible ways can you get a black card first and a black card second? But can you count all possible combinations? And when I say combinations, I'm talking about all the possible combinations of selecting one card and then selecting another one. Think about it. You could get an ace of hearts and another ace of hearts. You can get an ace of hearts and a 2 of hearts. So you need to think about all the possible combinations to come up with the sample space. We're not going to do that method. I'm just saying that it is possible for us to think of it that way. Okay? Here, we're going to ask ourselves, are the events independent or dependent? So here, you're going to pick a card, and then you're going to put it back, and you're going to do it again. Are those events independent? The events here are independent. Why? Because the first card is replaced back into the deck. That means that the second pick is not affected by the first. That means we can use the multiplication rule. The probability of black first and black second is equal to the probability of black first times the probability of black second. So what is the probability of picking a black card first? Well, we have 26 black cards. We're going to divide 26 by the possible number of outcomes in the sample space, which is 52. 26 divided by 52 is the probability of selecting a black card. Now let's multiply by the probability of selecting a black card second. Since you're replacing the first card, we're back to having 52 cards. We're back to saying, well, how many black cards do we have? We have 26 black cards. We're going to divide 26 by the number of outcomes in the sample space. That is 52 cards. If we go ahead and multiply, we should be getting 1 over 4, which is equal to 0.25. That is 25%. Here you have another problem where we find the probability of A and B using the probability of A times the probability of B. Now let's look at the same problem, but now we're not going to be replacing the first card. Here we're still trying to find the probability of black first and black second. Now let's just go straight into asking ourselves, are the events independent or dependent? In this case, the events are dependent. They do affect each other. Why? Because the first card is not replaced. It is not being replaced back into the deck. That means that the second pick is affected by the first pick. Now, let me go back to part A just to emphasize what we're seeing. We're seeing that in part A, the events don't affect each other. That means they're independent. And so let's make sure that we make that connection. If events are independent, they do not affect each other. Now, if the events are dependent, the events do affect each other. In this case, the second pick is being affected by the first pick. So what are we going to use this time? It's going to be similar to what we had above, but here at the end, when we're calculating the probability of black second, we're going to write, given that we picked a black first. So let's go ahead and think about this. What is the probability of selecting a black card first? Well, this is going to be the same as what we did above. We have 26 cards that are black. We're going to divide by 52. 52 is the total outcomes in the sample space, the total number of cards. Now, we need to multiply by the probability of black second, given that we pulled a black first. How are we going to calculate this probability? Well, let's think about it. For the first pick, you're going to imagine that you pulled a black card out of the deck and you're not replacing that black card. So how many black cards do we have left if you took one out? Well, we have 25 black cards left. Now, how many cards do you have left in total? You have 51, again, because you pulled one out and you didn't replace it. To calculate the probability of a black second, given that you pulled a black card first, we're going to write that we have 25 black cards. We're going to divide this number by 51. Go ahead and type this on your calculator and let's round to 4 decimal places. So we should have 0.2451. And then go ahead and turn it into a percent. Remember, to go from a decimal to a percent, you simply multiply the decimal by 100. You should have 24.51%. This is the end of our lesson. I'm going to be attaching an additional problem to this activity. Go ahead and look at that problem. That problem is also going to have some solutions, detailed solutions, to help you understand probabilities a little bit better. Keep in mind that probabilities are one of the most challenging concepts in this class. And so if you have any questions, you have the Q&A discussion board where you can pose a question. You have student help hours. We have a tutoring center that provides tutoring via Zoom and in person for free. Do not struggle by yourself. Do not spend hours looking through YouTube videos. Just come and use us as your resource.